Welcome to this explainer. We're constantly hearing demands for perfectly unbiased algorithms, right? But what if I told you that mathematically speaking, absolute AI fairness is literally an impossible illusion? Today we're diving straight into the fascinating, strictly bounded reality of machine learning. Because as we're going to see, the science actually tells a much more complicated story than just saying, hey, make this algorithm fair. It's a story of hard numbers and necessary sacrifices.
So let's kick this off by asking a seemingly obvious question, one that actually masks a super complex series of policy trade-offs. What does it actually mean for an AI to be fair? I mean, it sounds like a simple ethical question you'd ask a philosopher, doesn't it? But in machine learning, fairness isn't a gut feeling. It's a rigid mathematical definition. And depending on which definition you go with, an AI evaluating a loan or a resume can be deemed completely fair by one standard and just hopelessly unfair by another.
Here is our roadmap to demystify all this. We'll quickly cover defining AI fairness, the impossibility of group fairness, the individual fairness standard, counterfactuals and causal graphs, and finally, the latest breakthroughs in fairness tech.
Section 1. Defining AI fairness.
Now, what's truly fascinating here is that fairness isn't just some simple checklist. It's actually a deliberate policy choice between three structurally different and honestly conflicting standards. There's no magical, universally optimal standard just waiting to be discovered out there. You have to actively choose your standard based on the specific real-world context of your problem. Like, if you're designing software to screen medical patients, the metric you care about might be entirely different than if you're filtering job applicants. It all boils down to a human policy decision, not just a statistical one.
Moving right along to Section 2, Group Fairness and Impossibility. Okay, so group fairness looks at the big picture. It's all about making sure averages balance out across different demographics. Think of it like ensuring the overall approval rate for a bank loan is equal across different populations. It completely ignores the individual in favor of the macro view. When you use this standard, you're not asking if John or Jane were treated fairly on a personal level. You're really just asking if Group A and Group B, on the whole, got equal outcomes.
And to actually achieve this group standard, we typically look at three specific metrics. First, demographic parity, which just means equal acceptance rates across all groups. Second, equalized odds, meaning you have equal true positive and false positive rates, regardless of the group. And third, conditional use accuracy, which demands equal predictive values across those groups. Now, it sounds fantastic on paper to want all three of these simultaneously, right? I mean, why wouldn't we want a model that hits every single mark of group equality?
Well, here is the harsh reality, the mathematical brick wall, if you will. If underlying base rates differ, meaning the actual real-world prevalence of whatever you're measuring varies between groups, you literally cannot mathematically have demographic parity, equalized odds, and conditional use accuracy all at the same time. This is the impossibility theorem, famously established by Choldakova and the KMR team back in 2017. You are completely forced to choose your trade-off. Unless the underlying real-world data is perfectly identical across groups, absolute mathematical fairness across all these metrics is just an illusion.
All right, on to Section 3, the individual fairness standard.
Because hey, if we can't perfectly balance those broad macro groups, maybe we should focus our lens entirely on the individual, right? Unlike group averages, the individual standard, which was established by Dork and colleagues in 2012, dictates that similar people should receive similar decisions. Imagine your resume getting tossed out by an algorithm while another applicant with the exact same education, skills, and experience gets an interview. The individual fairness standard exists to stop exactly that from happening. It shifts the entire paradigm away from those broad demographic buckets and zooms right into a highly granular case-by-case comparison.
Now, this relies on something called the Lipschitz condition. I know, it sounds like scary math, but it basically just guarantees that the difference in the AI's decisions between two people won't exceed their actual real-world differences. But here's the catch. You have to mathematically define a similarity metric, represented by the letter D. And who decides what exactly makes two people similar enough to deserve the exact same outcome? Is 5 years of experience at a startup similar to 3 years at a Fortune 500 company? Well, that brings us right back to a deeply subjective human policy choice, just masquerading as pure statistics.
Let's jump to Section 4, Counterfactuals and Causal Graphs.
This introduces our third and final family of fairness standards, and it takes a slightly more philosophical turn. Introduced by Kuznets in 2017, this concept basically asks us to step into an alternate reality. The core question is this: would the bank loan still be approved if the applicant's gender or race was counterfactually altered? A decision is only considered counterfactually fair if the answer is that the outcome remains entirely unchanged under that alternate reality scenario.
But to test this alternate reality, you have to build a causal DAG that's a directed acyclic graph. Essentially, it's a hand-drawn map of how variables influence each other in the real world. Like, does your zip code influence your income, or does your income influence your zip code? This means this highly rigorous mathematical fairness standard is really only as justified as the causal model you explicitly choose to draw. If your map of how the world works is flawed, well, your counterfactual fairness measurement is going to be fundamentally flawed right alongside it. And there is another massive hurdle here. A recent theoretical result from NARIPS 2024 proves there's an inherent trade-off. Converting an optimal but unfair predictor to be counterfactually fair is inevitably going to cost you predictive accuracy. You literally have to sacrifice some of the AI's overall correctness, making it less accurate for everyone across the board, just to achieve this specific type of fairness. It's absolutely a zero-sum game between precision and counterfactual equality.
Finally, let's look at Section 5, Breakthroughs in Fairness Tech.
Let's talk about the cutting-edge tech from 2024 attempting to solve these exact legal and mathematical hurdles. Now, we just talked about changing a sensitive attribute to test an alternate reality. Well, legally speaking, in classification law, you can't just digitally flip someone's race or gender in a database to test an alternate reality. It is a massive legal and compliance headache, mainly because the law often strictly restricts directly using or manipulating those protected categories in any step of the decision-making process.
To fix this, a really interesting January 2024 paper introduced a brand new paradigm called backtracking counterfactuals. So instead of asking, what if this person was a different gender, it flips the direction entirely. It reasons backward from the outcome to the actual features. It asks what combination of the individual's actual, non-protected features would have produced that same counterfactual outcome. This is a huge deal because it totally sidesteps the legal objection since you're never directly intervening on the protected attribute itself.
On top of that, some really cool ICLR blog posts recently reconciled these massive concepts. Remember how we said earlier that a model could be group fair but counterfactually unfair? Well, the 2024 research shows that if you have an accurate causal graph, the apparent opposition between group and counterfactual fairness is mostly a mirage. It's just caused by unclear modeling. They aren't total opposites at all. They're actually just different facets of the exact same underlying causal structure.
However, and this is a pretty big however, this brilliant philosophical reconciliation doesn't erase the impossibility theorem we discussed earlier. Unequal base rates will always prevent total mathematical harmony among the three group criteria. We still simply cannot have demographic parity, equalized odds, and conditional use accuracy at the exact same time when base rates differ out there in the real world. That rule stands firm.
So as we wrap up this explainer, I want to leave you with this provocative thought. Since we literally cannot mathematically have it all, and total fairness across all metrics is technically an illusion, the burden falls entirely on us. How will you choose the standards, the similarity metrics, and the causal graphs that will shape the AI systems governing our future? The math won't save us from making hard choices, it just illuminates exactly what those choices are. Thanks for joining me on this deep dive.